our week 7. It's amazing how fast time flies when you're having fun. Next week, we have 2 final exams. The theory final will be on Tuesday, and the lab final will be on Thursday. Just to recap where we are with respect to this evening's activities, we will be talking about the review of the practice final, pages 1 through 3. And pages 1 through 3 on the original document had question 47 as being the very last question. So there were some questions that had come up on Discord, and I can see where those questions have come up as students have used, some students have used the word processing document, the Microsoft Word document, and started typing in their answers. And depending upon how much they typed in, the typed in responses pushes questions further and further down the page. And so some people kept on typing. When they saw the end of page 3, they had typed in so much stuff that they were still on question number 41, and they stopped. And I sent them messages on their practice file. So wait a minute, the original document had questions up through number 49, and you're responsible up through question 49 on the original 3 pages, irrespective of how you have typed in your responses or done illustrations or things of that sort. So hopefully that's been clarified, and I am looking for questions up through 49 on the practice final. So let's go ahead and take a moment and talk about those questions and make sure everybody has a good understanding as to how to resolve those. Let me pull that out. Practice final, pages 1, 2, 3. Okay, let's see what we got. Okay. So let's go ahead and begin the review on question number 1. In the electron current model, from blank side to blank side of the voltage source will be the direction of current flow. For question number 1, what were your responses? Let's go ahead and see if I can do this alphabetically. Luis, what was your response for number 1?
I got it from positive to negative is the direction of current flow. For question number 1, for electron current flow would be incorrect. Electron current flow always flows from the negative side of the voltage source through the circuit to end up back at the positive side of the source. So be sure to correct that, okay? So question number 1 is negative to positive. Question number 2, conventional current model flows from blank to blank. And what would be your response on that, Jess?
I just hopped on. What homework are we looking at?
Oh, we're looking at the practice final. I just want to get through reviewing the practice final real quick.
I believe that in conventional it would flow from positive to negative.
Your belief is correct. It does flow from positive to negative. Thank you very much. Question number 3, blank, blank. Blank are the subatomic particle or particles that exist within the nucleus of Bohr's model of the atom. Your answer to that, Harpreet?
It's neutrons and protons.
Neutrons and protons would be correct for number 3. Question number 4 goes to, and he's not here yet. Question number 4, Erica. What are the subatomic particles that exist outside the nucleus of Bohr's model of the atom?
Electrons.
Electrons would be correct. Thank you. Question number 5. Blank are the subatomic particles that are positively charged. Question goes to Toan. Is Toan here? Yes. Go ahead, Toan.
Proton.
Protons are positively charged. That's correct. Question number 6 goes to Javi, but Javi's not here yet. Question number 6 goes to, that person's not here yet. How about Andrew? Andrew's not here. My God. Tony. Number 6. What's negatively charged?
Electron.
Electrons are negatively charged. That would be correct. Thank you. And question number 7. Which subatomic particles are not charged? Ryan.
Neutrons.
Neutrons are not charged. Question number 8. Blank electricity are charges that are flowing in a circuit. Anna, what was your answer for number 8?
Current.
Current is correct for number 8. Question number 9, blank electricity random charges that are not flowing in a circuit. That question would go to Dana.
Static.
Static electricity would be correct. Thank you.
I
And
have a question. So for some reason, I thought that those two questions were true and false. Would that be incorrect to say? So I thought it was asking, is electricity random charges that are not flowing in a circuit? And I put false because.
Oh, okay. Yeah, we're looking for, just to be clear, going into the final exam, it's not a true false. Yeah, if it would be, no, not. Yeah, so I'm looking for the type of electricity, so current or static. Okay.
Okay.
Question number 10. Let's take a look and see, is Carlos with us? Not yet. Ephraim, you're with us now. So question number 10. What is the most common method of creating static electricity? Ephraim.
Friction.
Friction would be correct. Thank you. Question number 11. Blank is defined as the pressure to move electricity. And that question goes to, let's take a look here. Ben, no. Chisamaga. Question number 11. What's defined as the pressure to move electricity?
Voltage.
Voltage would be correct. Thank you. Question number 12. Blank is defined as charges in motion. Gregory Pella, what would you have for number 12?
Current.
Current is correct. Question number 13. Something is defined as opposition to electricity flowing. Francisco, what do you have?
Resistance.
Resistance would be correct. Question number 14. Can there be electricity flowing without a voltage source? And the question goes to, let's take a look. Abbas.
No.
The answer is no. There cannot be any electricity flowing without a voltage source. Question number 15. Can there be a voltage source without electricity flowing? And that question goes to, let's come back up here and see if some people have signed on. Not yet. Okay, then back up to the top. Luis.
For 15, yes.
Yes, there can be a voltage source without any electricity flowing. That is known as your famous 9-volt battery. Here's voltage without any electricity flowing. Good job. Thank you. Question number 16 goes to Carlos Navarro. Question number 16. The omega symbol represents what electrical quantity?
Resistance.
The electrical quantity, resistance, and units of ohms, yes? Ohms is the unit of resistance. Good.
Yes.
Okay, great. Number 17, 18, and 19 was very interesting, and I made note of comments on all of your practice finals that have been submitted today that we're looking for something specific. If you just say increase or decrease, that's like half the story. If I was specific, and let's go through number 17, for example. It says, if voltage remains the same, current blank, if resistance is doubled. Well, what was the change in resistance? The change in resistance wasn't increased. It was increased by how much? Increased by 2 times. I use the word doubled. So you can't say decrease. You have to say by how much. Okay. So the answer for number 17, Jess, what do you have?
I wrote decrease, but I think the full answer would be decrease by half.
Decrease by half. Yes. So
I just didn't write it because there wasn't a lot of space there.
No, it's okay. We would just simply write down HALVED.
Halved, okay.
Halved, yes, okay. And that would fit in the space. And that's what I was looking for, all right? It would be halved. Good job. All right. Yeah, that's fine. Number 18, we're going through the practice final. Number 18 on the first page. The question will go to Kirsten. So if resistance remains the same, current will blank if voltage is doubled. What will happen there, Kirsten?
If resistance remains the same, current will double if voltage doubles?
If voltage double, then current will double. That is correct. Thank you. Question 19, if current remains the same, voltage must be blank if resistance is doubled. So that question would go to Tony.
Double.
Current would be doubled. Voltage must be doubled if resistance is doubled. That's correct. For number 19 is doubled. Thank you. Question number 20, voltmeters must be connected somehow in order to measure volts. So what did you have for question number 20, Harpreet?
Parallel.
Parallel is correct for number 20. So that completes our first page. Are there any questions on that first page? Okay. Question number 21. Ammeters must be connected in blank to measure amps. So that question goes to Ephraim. How must ammeters be connected?
Series.
In series would be correct for number 21. Question number 22 goes to Erica. Can you get an electric shock by contacting a single point?
Yes.
And how would that happen?
For example, if you touched a statically charged balloon, you'd still get shocked.
If you touch a statically charged balloon, you would get zapped. Okay, that would be correct. The general point of the answer is to say no, that in order to get an electric shock that would cause you, and I'll rephrase the question in the future, but in order to get an electric shock that would cause you injury, you would have to be contacting 2 points. And the best example of this is how often when you've looked outside your room or looked outside your building and you look at, how many of you recall seeing birds on high voltage lines? Pigeons, seagulls, they're sitting on high voltage lines and they're sitting on 480 volt voltage lines. Why aren't those birds fried to a crisp and fall to the ground like fried chicken? They're still touching voltage, but they're touching voltage at one point. Now, if that wire were to fall to the ground and you go to touch it and your feet are not properly insulated, yes, that shock would enter your hand and go through your body, exit your feet to ground, especially if you were wearing thin-soled shoes, you would be electrocuted. So the thrust of the question is, yes, you can get shocked if you touch a single point, and the example would be a statically charged balloon, or if you jam a screwdriver into the hot leg of the AC receptacle, you would get a sting. Would it kill you? Not unless some other part of your body completed the circuit. Okay, so I will rephrase it so that, can you be injured by an electric shock contacting a single point? In that case, no, you can't be injured. You will not die. Maybe I'll rephrase it that way. Can you get killed if you contact at a single point? Okay. So the key thing here is voltage always flows between how many points? 2 points. And it takes one hand on the wire, one hand on something grounded, or one hand on the wire and your feet grounded, and the electrical current will flow through your hand, across your heart, stop your heart, through your feet, and that's the end of it all. All right. Number 23, question goes to Toan. Your bathroom GFCI wall out. Question?
Yeah, is the answer no for that? Because I put no.
The answer is yes and no based on the ambiguity of the question, and I said that I would rephrase it.
Sounds good.
Okay. Number 23, your bathroom GFCI wall outlet will trip when? Question goes to Toan.
Shorted.
Yeah, specifically what shorts? Yeah, and so the GFCI is called the ground fault interrupter, ground fault circuit interrupter. And what it is, what a ground fault is when there is specifically a short between the hot wire of your electrical outlet, which is of the 3 prongs that you see on the electrical outlet, it's the skinny short one. That's the hot wire. And if that gets in contact with ground, that is called a ground fault. And typically that can happen if you happen to have a hairdryer that is at the edge of the wash basin, and the wash basin is filled with water. You drop the hairdryer in the water, or worse yet, in the bathtub, and what will happen is the electricity goes immediately between the hot wire and ground. When that happens, hopefully your GFCI outlet will trip like a high-speed circuit breaker. It'll trip faster than the circuit breaker that's built into the walls of your apartment building or home, and it will immediately stop that rapid flow of electricity from injuring somebody who might be in the vicinity. So it is a short, but specifically a short between the hot wire and ground, okay? It is known as a ground fault, all right? All right. Question number 24. Number 24, you should be using what engineering prefix? Andrew, 24.
Milli.
Would be milli. It would be lowercase m, or you would spell it out as M-I-L-L-I. Okay, great. Number 25. Question goes to Kirsten. What engineering prefix is used for number 25?
Sorry. That would be pico.
That would be pico. Correct. Thank you. Number 26. What X would be evidence there? Question goes to Ryan.
10 to the -6.
10 to the -6 would be correct. Number 27. What exponent would be evidence there? Anna?
10 to the 9.
10 to the positive 9th power. That would be correct. Number 28. Can you be electrocuted in pure water? Dana?
No.
And that answer was?
No.
That answer is no. You cannot be electrocuted in pure water. So you need electrolytes. So some kind of mineral content that would be able to carry the electrons. Okay, very good. Next, number 29. And about 25% of you missed this, maybe because we have, you read the question too quickly, or you don't understand how a potentiometer works. So question number 29, question goes to Carlos. What do you have?
Sorry, I need to pull up my, I don't have it in front of me, Professor.
Hey, Chisamaga, what do you have for number 29?
I have 2 milliamps.
And 2 milliamps is, you fall into that 25% of our friends. So let's read this through carefully. It says you have a 5 kilo ohm potentiometer adjusted where?
To its midpoint.
To its midpoint. And what is a potentiometer? A potentiometer, class, is a variable resistor. And if that variable resistor is adjusted to its midpoint, we're only using half of its resistance. So if its total resistance is 5K ohms and we adjust the potentiometer to midpoint, we're only using half of 5 kilo, which is 2.5 kilo. So if you take a 10-volt source and you divide by 2.5 kilo, you're going to end up with what answer there, Gregory?
4 milliamps.
4 milliamps would be correct. Okay. So everybody who had missed that, be sure you read the exercise very carefully about where the potentiometer is adjusted to. Okay. All right. Question number 30. Blank is the resistance of a potentiometer in a circuit with a 15-volt source and 10 amps flowing. Question goes to Francisco. Frank, what do you have?
1.5 ohms.
1.5 ohms is correct. Thank you. Question number 31. Now, this was very interesting. About half of you got this right. Half of you got this wrong. So question, Abbas, what do you have for number 31?
$75 volts.
Did you say 75 volts?
Yeah.
75 volts would be incorrect.
Oh.
What should it be, class?
Negative 75.
Voltage drop. Negative 75 volts.
Oh,
As you look at that circuit, who would like an explanation as to why it is negative? Can
The
you see
red
why it
end.
should?
The red end of the probe is connected to the negative side of the voltage.
Precisely. It says the red probe is connected to the bottom of R1. It is physically connected to the negative side of the voltage source. The black probe is connected to the top of the circuit. It's connected to the top of the voltage source. Your voltmeter can only read negative 75 volts, okay? So you miss a polarity, that's half an answer. So be mindful of your polarities, okay? It's the difference between positive quantity versus negative quantity. So let me give you an example. The government assistance checks, as they've come for some people for unemployment, a bonus $600 a week. Is there a difference between positive $600 in your bank versus negative $600 in your bank? You betcha there is, because you for sure don't want to see all of a sudden the next day negative $600 on your balance, right? So is there a difference between positive versus negative? So if the answer calls for a negative sign, you must put down a negative sign, or it's what? Half or all wrong, depending upon the quantity you put down. Are we clear on that, everybody? Okay. Question number 32. Number 32 goes to Luis. Luis, what do you have for VR1?
I got 75 volts.
And is that positive or negative?
Positive.
Yeah, you're correct. When we're looking at voltage across a resistor, you're not told specifically where the red probe goes. You're not told specifically for question number 32. If it simply says VR1, we can measure that red probe on top. We can measure that red probe on the bottom. So all you can do is just simply put down positive 75 volts, okay? If you are told specifically the red probe is on the bottom, okay, if I gave you letters A and B, then you would put down the appropriate polarity. Question number 33. Question number 33 goes to Luis.
For 33, I got 35 volts.
35 volts for VR2. I saw some interesting numbers from several of your classmates. And if you think about it, take a look at the schematic. And we should all be looking at page number 2 that you should have printed out, or at least looking on your screen somewhere. And what do you have in the second branch? In the second branch, you have 35 ohms and you have 40 ohms, yes? Are they in the second branch? 35 ohms and 40 ohms, yes? How much voltage do you have across those 75 ohms? 75 volts. Does it stand to reason that if you've got 75 volts across 75 ohms, that means each ohm drops a volt? So if the first resistor, R1, is 35 ohms, does it stand to reason it should drop 35 volts? Okay, you can prove it to yourself by using a VIR table if you want to go to that extent, or you can think using Mama's calculator that I've got 75 across 75 ohms. I probably have a volt per ohm, so it should be 35 volts. Question number 34 goes to Jess. What's the RT that's calculated?
I have 30 ohms.
30 ohms is correct. Thank you. Yeah, I saw some other interesting numbers for RT, and it's not going to resolve to anything other than 30 ohms. Your right branch, 35 and 40 ohms combines to be 75 ohms, yes? So you have 75 ohms in parallel with 50. That's a quick reciprocal calculation to get to an R total of 30 ohms, all right? Question number 35 goes to Harpreet.
2.5 amps.
2.5 amps is correct. 36 goes to Ephraim.
1 amp.
1 amp is correct. Question number 37 goes to Erica.
I got 1.5 amps.
1.5 amps is correct. Any repeats or questions on the second page? Okay. Let's take a look at the third page. The third page brings us with number 49 at the bottom. So let's see how we do with this. Most everybody did pretty well on this series parallel circuit. Well, let's see what happens. So question number 38, the total resistance that was calculated is what value, Toan?
38 is 50 ohm.
Number 38 is 50 ohms is correct, 50 ohms, thank you. Number 39 is what amount of current, Kirsten? IT.
Sorry, I couldn't find my Zoom. Number 38 is
Number 39. Number 39.
500 milliamps.
500 milliamps is the total current calculated. That would be correct. And number 40, Andrew. Andrew? She stepped away. Tony, number 40?
500 milliamp.
500 milliamps is correct. Thank you. And number 41, VR1 calculated to be what value, Ryan?
19 volts.
19 volts is correct. Number 42, VR2 calculated to be what amount of voltage, Anna?
6 volts.
6 volts is correct. Number 43, VR3 calculated to be what value, Dana?
43?
Number 43, yes.
6 volts.
6 volts is correct. Thank you. Number 44, IR2 calculation. Carlos?
$500 milliamps.
Well, 500 milliamps is the total of the circuit. So 500 milliamps is going into parallel circuit. That means part of the current is going to be split to go through R2. Another part of the current is going to be split to go through R3. So we couldn't have all 500 milliamps just go to one side. It's going to be split. So we're looking for how much is split through R2 and R3. So for number 44, could you give that one to us, please? Question goes to Chisamaga.
44.
44, yes.
I got 300 milliamps.
300 milliamps would be correct. If you do a current divider, you should be able to calculate 300 milliamps for IR2. Number 45 calculates the what current for IR3. Question goes to Gregory Pella.
I got 833.33 milliamps.
You're reading 45 because 833.33 is the frequency on the next question. And it's just odd that number.
I think I put it in the wrong box.
Yeah. So what do you have for number 45? I'm looking for a current. Or you put the 833.
Yeah, that's
okay.
what I meant.
All right. So Francisco, what do you have for number 45?
I didn't get that far.
Okay. Question goes to Abbas.
200 milliamps.
200 milliamps would be correct. Okay, 200 milliamps is correct. Okay. Now we have an oscope display. And the oscope display, most people were able to do the amplitudes correctly. Some of you had some challenges with respect to period and frequency. So with respect to amplitude, and let me just read off to you, you can be within a few millivolts of these numbers. It just depends on whether you took that measurement at 2.4 divisions or 2.5 divisions, okay? So let's stay with 2.4 divisions for the peak. If you count and draw a ruler and counted it at 2.4, you get one set of numbers. If you counted it as 2.5, get another set of numbers. Either one will work. So the V peak can be, and let me see if we can change this up this way. Go here, and let's see. Where is this guy? Oh, I see what's going on. Let's go ahead and take this and plug this in over here. And have it come up as an option. Video. System is thinking. Okay, I want this, and which means I have to flip this around this way, have this up here, and focus. Cool. All right, and let me go to speaker view. All right, you should be looking at something very similar to these numbers. If you counted this waveform as 2.4 divisions, you would have 36 millivolt peak. If you counted this as 2.5 divisions, you would have something 37.5 millivolt peak. You shouldn't have anything lower than 36 millivolt peak. You should not have anything higher than 37 millivolts, 37.5 millivolt peak. Either one of these two numbers or something in between, okay? If you counted this at 2.4 divisions, 36 millivolts peak, you double that to 72 millivolts peak to peak, would work out to be 25.46 millivolts RMS, 22.92 millivolts average. If you counted this as 2.5 divisions, 37.5 millivolt peak, 75 millivolt peak to peak, RMS is 26.56 milli V RMS, V average 23.87 milli V average. So before I talk about the period and frequency, are there any questions about how to read the peak value? Because I can help you now, I just can't help you during a test.
Hey, Professor, for 26.52 for VRMS will be fine.
I understand. So your VRMS, but what did you take for the peak? Did you have 37.5 milli V peak?
Yes, I did.
Okay, so if you have 37.5 milli V peak, so on the calculator, we will do this. So 37.5 exponent -3. Okay, so there's my 37.5, and I'm going to multiply that by the square root of 0.5, yes, in order to get an RMS. Hit engineering, and what does my calculator show, and what does your calculator show? It should show this, 26.516, which that 6 compels you to round this to 26.52, which is what I have here.
Thanks, thank you.
Okay, okay. So the most common error for people who have gone in this route is they forgot 0.5. I saw a number of calculations for the RMS and V averages that were wrong because instead of keying in 37.5 milli, they keyed in 37 milli real quick, and then therefore these two numbers ended up different than what's on this paper now, okay? So be very careful of that. All right, good question though. Any other questions regarding how to read the peak value of this waveform? Okay, now let's take a look at period. What was the definition of period? Question goes to, let's take a look. Chisamaka, can you give me the definition of period, please? What do you recall, the definition of period?
It's the time for one cycle.
Precisely, it's the time for one cycle, which means if the cycle begins here on this dot, it goes up to a positive peak, that's 90 degrees, positive 90. It comes down to 0 volts, so that's 180 degrees. It comes down to a negative peak, so that's 270 degrees. And then it comes back up to 0 volts, and that's 360 degrees. One complete rotation of a waveform is 360 degrees. So we have no business counting both sine waves. We only count one complete sine wave, which is from here, 1 division, 2 division, 3 division, 4 divisions. Are we clear? There's 4 divisions for one cycle, everybody. And if you take 4 divisions and you multiply that by 300 microseconds per division, you should end up with what period? Question goes to Luis.
I got 1.2 milliseconds.
And you should end up with 1.2 milliseconds. That would be correct. Which then, because I saw some people end up with 2.4 milliseconds because they were counting both waveforms. You don't count both waveforms. You only count a single waveform, a single cycle, because that's what period is. Period is the time for one cycle, okay? And so it's 1.2 milliseconds. And based on that, the frequency works out to be what, Jess?
Um, 833.33 hertz.
833.33 hertz would be correct. Thank you. All right, then the rest of this is pretty straightforward. 85 volts for here, 85 volts for here, 5 microfarads, 45 microfarads. When they're in series, you don't add these in series. For total capacitance in series, you use reciprocal method or one of the shortcuts. And in this case, I use one of the shortcuts, end up with 5 microfarads. When they are in parallel, you do add the numbers. So 3 15 microfarad capacitors will total to be 45 microfarads. And that brings us up to question number 49, which ends the first page. Are there any questions or repeats on the third page?
I have a question on 47.
On number 47, yes.
So since it's volt RMS, don't you have to divide by the square root of 0.5 to get the V peak, or is it not?
That's a very good question, Luis. No, you don't have to. In fact, the RMS, the reason why RMS is the standard of the industry for all of your markings on the back of your computers, on the back of your toasters, ovens, the back of your microwaves, on the back of the little power supply that charges your cell phone. RMS is the standard of the industry for giving us an ability to measure using a digital multimeter to be able to measure between these two probes a very specific non-changing value on this display. So when I take these two probes and I hook them up to a wall outlet, that non-changing display will be somewhere between 119 to 121 volts RMS. And the reason why it's slightly different between 119 to 120 to 121 is depending upon the load of what's happening in your neighborhood. PG&E promises their best to give us 120 volts, but depending upon the electrical needs of your neighborhood, it might be a little less, it might be a little higher. So I've measured less than 120 volts in my outlets at times, and I've also measured more than 120 volts on my outlets at times. But the standard of the industry for your utility bill from PG&E and for all of the markings that we have on any plug-in for electricity will always be in some form of RMS. So in the house, we have 120 V RMS for most of our wall outlets. We also have in certain parts of our house, in the kitchen, the wall outlet is 240 V RMS. In the laundry room where you have a washer and dryer, that's a heavy appliance, that is also 240 V RMS. And if you happen to have an air conditioning unit outside of your living space, the air conditioner also requires very, very often 240 volts RMS. So all the standard of the industry is in RMS so that we can measure a consistent singular value. Yes, the waveform comes to us as a waveform, and if this was 120 volt RMS waveform, if you divide by square root of 0.5 instead of multiply, so 120 divide by square root of 0.5, that would give you 169.70 volts peak. Right there, I've calculated that many times. So the waveform, if we were to hook up your O-scope to the wall outlet, we would see a peak at 169.7056 volts peak. We would actually see it peak on the O-scope, that value. However, if we measure with this instrument instead of the O-scope, our measurement here will be in RMS, and this is closer to 120. So why RMS? We said before on a previous PowerPoint slide that RMS is the equivalent AC that would cause a device to dissipate heat or create the same brightness as that same number of DC volts. So if we were to hook up a DC voltage source to a bulb that would be able to accommodate DC, then it would take 85 volts in order to create the same brightness or heat output, okay? So that's where we stand with respect to RMS versus volts peak. Good question. Any other questions that anybody has between pages 1 through 3 on our practice final?
Are you able to go for the first two, please?
Am I what?
On the first page, the first two?
What about the first two? What about the first two?
I didn't get the answers to those, so I just wanted to confirm.
They're right here. Take a look.
All right, thank you. I got it. Yeah.
Okay, any other questions? Is this your chance to ask? Okay, so pages 4, 5, and 6 are due no later than 6 o'clock on Thursday. I will review those with you, and also some other things that are not on the practice sheets that will also be part of the final that we'll be talking about tonight. All right, so nothing further here. Let's All right, let's talk about a very important component that we're going to use, and that's known as transformers. That's an N.